Welcome to our channel of Sciences and Mathematics. Our topic for discussion today is going to pertain to the sample question that we have given on the board. And this has a relationship from the de Broglie's wavelength. And of course, it's going to be associated with the description of an electron that is being accelerated in a potential difference. And we're going to see that there's a relationship between this and the one that we have discussed in our previous video. I'm trying to find the de Broglie's wavelength. So for that case, thank you and welcome. So as I've said, today we're going to look at another topic, of course, in quantum mechanics. And this is the de Broglie's wavelength. And of course, the speed of that's a subatomic particle, which is an electron that is being accelerated in a potential difference. So in this case, as we said, de Broglie advanced a relationship, which is an equation that, of course, he advanced from the Einstein-Mass relationship, whereby it was given as the de Broglie's wavelength is equals h over m. This is the speed of a particle, maybe if it's an electron. Therefore, we're going to use that. So this is a Planck's constant. This is the mass of an electron. Mass of electron or as a small particle. And then we have this is the speed. So therefore, using this relationship, we're going to see how we can be able to solve our equation. But there's also a relationship that we're going to exploit in this, given that we have been given some constants. And in this case, I'm going to read what is the speed and the de Broglie's wavelength of an electron that has been accelerated by a potential difference of 300 volts, given mass of electron 9.1 times 10 negative 31 kgs, Planck's constant 6.626, 10 negative 34 joule seconds, E charge of an electron 1.6, 10 negative 19 coulombs. So therefore, we're going to use the quantities we have been given there in order to derive our relationship that is going to assist us to solve this equation. So therefore, in a potential difference, energy can be given as EV, but from the classical concept, we say that energy of a particle, kinetic energy, can be given as a half mv squared. So in this case, if this electron is being accelerated in a potential difference, it is moving with a specific kinetic energy. Therefore, we can have a direct relationship between how the potential energy of this electron can be associated with the kinetic energy. So therefore, when we say that there's a difference or a loss in potential energy, or there's a change in potential energy from the work energy theorem, that is direct translation to kinetic energy. Therefore, we can equate this and say EV is equals a half mv squared. So if we try to manipulate this equation, we can be able to come up with a concept to represent V, which is a speed. And of course, we are going to have V from this by just doing this one, EV equals a half, or we can just write by doing a multiplication of 2 on both sides, 2EV is equals mv squared. So therefore, we can do a substitution for V and find by interpreting this from this particular concept. So let's find the value of EV, given that we have been given these two specific information. So therefore, we can say that EV for energy is the same as 1.6 times 10 negative 19 times 300, which is going to give us 4.806 times 10 negative 17 electron volts. That is in the form of that energy. So if we do a substitution for that one in this, we'll get that this can be represented as 2 times this value, which is of EV 6, 10, negative 17, which is equals mass. So we are going therefore to do a substitution for this, for mass. Now remember there's a difference between this one maybe which might give us a confusion. This one is a potential difference which is V, and this is the speed. So therefore the first implication of maybe trying to cancel out does not come in this case. So therefore maybe I can just use this one. I can just maintain it for speed, but remember that this is a potential difference while this is speed. So therefore in us trying to find the speed of this, we're going to do mv squared. So therefore we can make v the subject of the formula by doing still a substitution. So 2 times 4, 8, 0, 6, 10, negative 17 is equals 9.1 times 10, negative 31 times v squared. So therefore v equals the root of, we take this one the other side, 2 times 4, 8, 0, 6, 10, negative 17, divide by 9.1, 10, negative 31. Now this is going to give us our just a minute. So this is going to give us just indicate it somewhere because of space. So this is going to give us this is 1, and then let me just write it here. It's going to give us 1.027710 7 meters per second. So that is that will be the speed of that electron, that potential difference, and the de Broglie's wavelength will be given as the de Broglie's wavelength will be given as lambda equals h over mv, that speed. So this is 6.626 times 10 negative 34 divided by, this is going to be in meters, so therefore mass times 10 negative 31 times v, which is 1.027 times 10 power 7. So this is going to give us, 7.08 times 10 negative 4 meters. So in this case, going to be, no, this is going to be negative 3, negative 7. This is going to be 10, and then this one. So this is negative 11. So this is going to be the de Broglie's wavelength for this particular electron, which is the second part of our question. So in this case, this is how we are going to use this concept in trying to tackle all the questions that we may find maybe in quantum mechanics, or which are trying to find to describe the wave-particle duality that we said, which is of course our concept of the de Broglie's wavelength. So in that case, we'll have to stop there, and I hope that we have understood the concepts that we have been describing using this set of a problem that we have tried to solve on the board. So for that case, that is it for today. Thank you. Bye. God bless.